All right, welcome back again, everybody. Today we're going to be finishing chapter 2, finishing off with section 2.6, which is all about inverse functions. Inverse functions basically undo the process of a function. Let me pull up the slides, and here we go. Right. So we're going to do a very, very brief review of functions. I'm not going to dwell on it. Hopefully, they make a lot more sense now. Then we're going to talk about one-to-one or injective functions, talk about inverse functions. We'll define them. Then I got to give you some important notes just to kind of clear some things up. We're going to talk about a handy test called the horizontal line test. Might sound a little bit familiar. Then we're going to get an important result that we're going to need later on, has to do with what we had talked about in 2.4 about the need for strict monotonicity. That's going to come up right then. Then we're going to see a graphical interpretation of inverse functions, and we'll finish up with the cancellation equations. Okay, so quick review of functions. I'm not going to spend too much time on them. Remember that a function is just a rule that assigns to each element in the domain exactly one element f of x in the range, and it's basically a mapping from this set to that set. Just want to remind everybody about these definitions. Remember, the domain of a function is just the set of all the input elements that work. The range is the set of all possible outputs, and the codomain is just where the range lives. That's the basic idea, okay? Um, Remember, I had given this example of a function as a box, so you can still consider that, right? The box is labeled f. F says what to do to the things that you put inside of it. So you can drop x into the box. F operates on what you drop in, and then what comes out is f of x. And f of x is the output. Want to review this notation one more time. This notation is actually going to be really, really important for this section. So just remember whatever is in these parentheses is the input, and then F is the rule. And the big takeaway here is the whole symbol is the output. Okay, that's critically important for this section. F of x is the output, and you need to treat that symbol as a single object and an immutable object. You're just treating it as one symbol. So that means you can't start pulling off the F and the parentheses. That doesn't make any sense. F of x is the output of the function, okay? Keep that in mind. Um, I had given this example of 3x plus 1, where x goes into the box, it gets multiplied by 3, then you add 1. And when you do that, what you get out is 3x plus 1, and that is the output, f of x. All right? So this leads us to our motivating question. I'm going to ask you this. If we have a function f, does the process of working backward from the output f of x to the input x always constitute a function? Does that always make a function if you work backward? In other words, if you like reverse the process, is that a function? So I want you to ponder that for a minute. What do you think? Working backward, will that be a function if I work backward? Hmm. Okay, well, the answer is sometimes, but not always. All right. And so that's kind of the catch. Sometimes this will work, sometimes it won't. So to talk about that, we first need to talk about what are called one-to-one or injective functions. So here's the definition. A function is called one-to-one or injective if it never achieves the same output value at different inputs. Okay. More specifically, if you've got two different inputs in the domain, you will never have the output is the same. Okay, so that's what I mean by it never achieves the same output value at different inputs. Okay, that's a one-to-one function. Okay, so now what is an inverse function? So you got to start with a one-to-one function. So let f be a one-to-one function. Let's say its domain is A and its range is B. Then its inverse function is denoted by f to the negative 1. It's pronounced f inverse. Its domain is B, its range is A, and it is quite literally defined by this equivalence relation. So the inverse of f is defined as basically the backward transformation, the backwards function. So if f of x equals y and it is invertible, then f inverse of y equals x. And this will be true for any y in B. So that's the basic idea. This is another one where I want you to kind of stare at it for a minute. Just stare at this definition, try to understand what's going on with this equivalence here. Okay, and now I want you to read it out loud. Remember, you don't have to read it to anybody. Even better if you're watching this with a friend or with a colleague. Read it out loud to them, have them read it out loud to you, but just say something out loud. Okay, now let's talk a little bit more about it. I'm going to pull up this picture again and kind of add to it. So remember for a function basically takes things from its domain to its range, right? So here I have A, that's the domain of F, and here I have B, that's the range of F. And so F goes from its domain to its range. Now, if F is invertible, if it has an inverse function, the inverse function is going to go backward. So the inverse function is going to take stuff from here and map it backward to here. So F inverse would take Y and it will map Y to X in this case. So here, F is mapping X to Y. F inverse is mapping Y to X, just like so. Now, because of that, the domain and the range of an inverse function are opposite that of the original function. I don't know if you've noticed this, right? Here's the domain of F. It goes to the range. This is the domain of F inverse, and it goes to this range. So they get switched. That's the idea, and it's notated down here as well. Now, intuitively, I'd kind of mentioned this at the very beginning. An inverse functions undo the process of the original function. That's really what it's doing. So I want you to think of it like that. It undoes the original function. So for example, if the original function says to multiply by 3 and then add 1, 3x plus 1, then the inverse operation will be subtract 1 and then divide by 3. That would be the inverse function right there. So what I want you to notice is that the elementary operations and the order in which they are performed is inverted. Okay? All of that is inverted. Okay, now all that being said, some important notes. This can be a little bit tricky, but with enough practice, it'll become more clear. Once again, you just really got to understand inputs and outputs, what's going in, what's coming out, because now we're going to start switching them, all right? So inverse functions switch the domain and the range of the original function. That's one thing I just mentioned, right? So the domain of F inverse is the range of F. They're switched. And the range of F inverse is the domain of F. They're switched. Now, a notational thing, this can be kind of confusing until you get some practice with it, but the -1 in the exponent of this notation, it does not indicate reciprocation, okay? Let me zoom in on this. Here we go. So when we are speaking of inverse functions, I need you to understand that f inverse of x is not 1 over f of x. It really is not 1 over f of x. This may be kind of annoying because you're like, well, gosh, I just made sense of exponents and -1 meant to do that, and now it means something else. I get that that can be very frustrating. There is a reason why the notation appears this way. If you want to know about it, ask in class, we can talk about it there. But I just need you to understand that when we are speaking of inverse functions, it does not mean reciprocate, okay? It doesn't mean write it as 1 over f of x, okay? And why the notation was chosen to be this way will become more clear the further along you go in your mathematical studies. All right, so those are the important notes. Now let's practice it a little bit, okay? So here's an example. I do want you to try this one on your own, but suppose that f is an injective function, so it's 1 to 1, and suppose we know f of 1 is 5, f of 3 is 7, and f of 8 is -10. I want you to try to find f inverse of 5, f inverse of 7, and f inverse of -10, okay? Think about it for a moment. Right? Now, got to say something out loud. So say something out loud, maybe just the answer if you can see the answer already. And now try to work it out. Write it out on your own and find those values. Right, here we go. Let's do it together. This one's not as bad as it might seem. Once you get used to the notation, it becomes a lot more clear. So we're given these values, these inputs and outputs. But remember, inverse functions invert things. So the inputs and outputs get switched. Literally, they get switched. So f inverse of 5 is 1. And that's because f of 1 is 5. Wait, come back. Where is it? There it is. F of 1 is 5. F inverse of 7 is 3 because f of 3 is 7. F inverse of negative 10 is 8 because f of 8 is negative 10. That is the inversion relationship right there. That is exactly what this definition is saying. Where is it? This definition. F inverse of y is x because f of x is y. That's exactly what I was just saying here. F inverse of 5 is 1 because f of 1 is 5. That's the inversion relationship, so that's really what you need, okay? Okay, now let's do this. So let's try to find the inverse of a function where we are given this formula. Um, this is one where, okay, I will say this. You might already know a technique for finding the inverse of a function like this. I'm actually going to encourage you to try using a different technique, one of the ones that I introduce here. The reason is because I want you to get a lot of experience with this notation, and I want you to get really, really comfortable with the notation. And I also want you to get really, really comfortable with the ideas of inputs and outputs, okay? So this is one where um, I'm going to do it myself, and then you can compare it to the way that you might have done it if I had just said do it yourself. Okay, so here's the idea. First of all, this function is invertible because its graph passes the horizontal line test. We're going to get that theorem in just a minute here. Remember, not every function is invertible. This one happens to be invertible, so we can invert it. So to invert it, here is all you need to do, and I want you to take this to heart. Simply solve it for x. That's it. That's it. Solve this equation for x in that, solve that equation for x. Remember, x is the input, f of x is the output. So you treat f of x like a whole symbol. You don't start breaking apart f of x. You keep it the way it is. Just solve this for x. And then when you've done that, if you're able to do it, if it's invertible, then you've computed the inverse function. So here we go. F of x equals x cubed plus 2. I'm going to subtract 2. I'm going to take the cube root. So take the cube root of both sides. I get this. And now I've solved it for x. Here I just moved it to the other side to make it look pretty. So now I want you to understand you have inverted the function at this point. The function has been inverted. Here, this is an equation where if you put in f of x, you get out x. That is literally an inverse function. I put in the output, I get the input. We've inverted the function, right? So no funny business. You literally just solve for the input. Now for niceness, just to make things look pretty, we're going to relabel things a little bit. So we're going to say that because this is the inverse function, we're just going to relabel it as f inverse of x and change that to x. That's all you need to do. That's it. You may have seen techniques where you're substituting y and switching x and y. You don't need to do any of that. Just solve this for x and relabel at the end, and you'll be good. That's all you need to do. Okay, right. How about this one? So this is one that I do want you to try on your own now that you've seen me do one of them. And I want you to try to do it the way that I just showed. So keep f of x, keep x, and just solve this for x. Oh, I guess I kind of already said, okay, think about what I just said. Say something out loud. What are you going to do? How are you going to find the inverse of this? Okay. And now go ahead and compute it on your own, and then we'll do it together. All right, here we go. So remember, all we're going to do is solve this equation for x, remembering that f of x is its own whole symbol. Just treat it like a single object, okay? Here we go. All right, I need to isolate x. I need to merge these x's somehow in a valid way. So I'm going to multiply both sides by x minus 5. Maybe I'll write that here. X minus 5, x minus 5. These will cancel. And then now I've got this. Okay, looking good. Now, here's the catch. I've got x over here, I've got x over here. I need to get them together. I need to get them on the same side. So I'm going to distribute f of x to both of these terms to stretch things out a little bit. So then I'm going to get x times f of x and negative 5 times f of x. Remember, f of x is its own whole symbol. It's just a symbol, right? Hold it all together at once. Okay, now there's an x term here and an x term here. And I've got constant terms here and here. I need to get these two terms together, these two terms. So I'm going to move this to this side. Wait, oh, I'm sorry. I'm going to move this to this side and move this to that side. And I get this. There we go. Sorry, this isn't a constant term, my bad. Okay, now check this out. I've got an x in this term and I've got an x in this term, so I can factor them out. I can factor x out of both of those terms to get this. All right, we've almost fully isolated x. Notice that x is just right here. F of x is its own thing. F of x is its own symbol. Leave it alone. Now we're just going to divide both sides by f of x minus 2, like that. And then voila, we've done it. Notice here, x is isolated on one side, so we have now inverted the function. The function was invertible, we inverted it, we have computed the inverse, we have now performed the hard part. All that's left is to relabel things to make them look pretty. So here I go. F inverse of x is just 1 plus 5x over x minus 2. So I'm just replacing these with x. That's it. And then here I rewrote it just to, again, to make it look a little prettier. That's all. Um, so let me see. Oh yeah, that's right. That's right. To make it look a little prettier. So now what I want to do is I want to take a look at this graph on Desmos to kind of show you something. Let me pull it up here. Where'd you go? Where'd you go? Where did you go? Right here. Okay. Boom. Here we go. Okay. So I've actually got both of these graphs. So this was the original function we started with. Maybe I can move this a little bit. There we go. This is the original function we started with. And there's a couple things I want to point out. For one, there's a vertical asymptote at 5. We're going to spend a lot of time talking about those in chapter 3. But right here, there's a vertical asymptote. There also happens to be a horizontal asymptote at 2. So that's this one right here. Okay? Just like that. This graph, it passes the horizontal line test, as we're going to see in a minute, so it is invertible. And now what I want to do is I want to show the inverse. This is the inverse, okay? Click away from that for a minute. So the inverse here is in green. That's the inverse. And let's take a look at these. So this one actually has an asymptote at 2. Right? It's got an asymptote at x equals 2. There's a can't divide by 0, so x is not in the domain. There we go. And this one has a horizontal asymptote at 5. So notice there's like a relationship here between these two things. The original function had a vertical asymptote at 5 and a horizontal asymptote at 2. Its inverse has a vertical asymptote at 2 and a horizontal asymptote at 5. Okay, and there's a reason for that, and we're going to expound upon that right in a minute here. The reason is that the graph of an inverse is just reflected over the line, reflected over the line y equals x, this one right here. So what I'm going to do is hide some things. Here's the original function. Here is its inverse. So there's a symmetry going on, and we're going to spend basically the last bit of the last bit talking about this symmetry as well as an important result here. But literally, if you want to get the graph of an inverse of a function, you just reflect it across the diagonal line y equals x, and that is the graph of the inverse. That's all you got to do. So if you know how to graph a regular function, you know how to graph its inverse too. You just reflect like that. All right. And again, the reason, like here, here's x equals 5, when you reflect that line across the diagonal, you're going to get y equals 5. And when you reflect y equals 2 across the diagonal, you're going to get x equals 2. There it is. So that's where that reflection property is coming in. We're going to see it again in just a moment. Okay. Yeah. Oh, yeah. And then there's this important note. So the reason that that's occurring is precisely because the domain and the range are getting switched by the inversion, right? That's why those asymptotes are getting switched. Let me go back, right? That's why the asymptotes are getting switched. This is related to the domain of f. Now it's related to the range of its inverse. This y equals 2 is related to the range of f. Now it's related to the domain of its inverse because domain and range get switched, right? That's the idea. Okay, now let's talk about the horizontal line test. So this is a very quick visual way to tell if a function is invertible. So if a function is one-to-one, if and only if no horizontal line crosses the graph of the function more than once. So this is kind of like what we did back in section 2.1. But in other words, if any horizontal line intersects the graph of a function more than once, then the graph does not represent a one-to-one function, and therefore it is not invertible. All right. Um, yeah, so this is something we talked about in 2.1. If a graph passes the vertical line test, then the graph represents a function. If the graph also passes the horizontal line test, then it's one-to-one and we can compute its inverse. That's the idea. Okay, so here's a couple examples. Here's a graph that is one-to-one. It passes the horizontal line test. I kind of did this before, so I won't spend too much time on it. But you draw a horizontal line and you just see how many times it intersects the graph, right? Here it only intersects at once at any given time. Here, it intersects twice almost everywhere, right? Almost everywhere. So what that means is this graph is not the graph of a function that you can invert, at least not outright. Okay, now we got to talk about an important result, and this is one that I was building up back in section 2.4. So if f, where is it? There we go. If f is strictly increasing or strictly decreasing, then it is one-to-one, okay? If it is also continuous, then it has an inverse. This is an important result, okay? An important result. So what I'm saying here, yeah, a surprisingly powerful result. What I'm saying is imagine any continuous, strictly monotonic function that you've seen, it's invertible. You can find its inverse, you can graph its inverse, you can compute, well, you can, I'll say at least point-wise. Finding the formula for the inverse might be very tricky. Sometimes you can only do it point-wise, but the point is, if your function is strictly increasing or decreasing, and it's continuous, then it has an inverse, okay? And the other thing is the strictness is necessary, right? Let me give you an example. If you've got a graph of a function that looks like this, like we saw back in section 2.4, where it's got a constant interval right here, then it doesn't pass the horizontal line test, right? Do a horizontal line. Hey, come here. Do a horizontal line for this. There we go. Right here, it fails the horizontal line test. And the reason the horizontal line test tells us this is because what's happening is different input values for f are giving the same output value. That's a big problem because then when we try to invert the function, we're going to have an output value, whatever this output value is, and it's going to map to a whole bunch of input values, right? So that's the problem is you lose that relationship where functions only spit out one thing. This is the situation where if you tried to invert it, the inverse would have to spit out a whole bunch of things for just one input. Doesn't work. Yeah, it doesn't work. Okay. Now, just to kind of round things off geometrically speaking, this we kind of already saw, but because the domain and the range of an inverse function are switched from that of the original function, the inputs and outputs are switched. And so graphically, that means the x values and the y values are switched, quite literally. So here's an example. Let me zoom in on this one. Wait, do I say this? Yeah. Let me do this. Let me do the zoomable ones. Here, let me zoom in on this picture a little more. I wanted a little more. There we go. So here I've got the graph of y equals x cubed. This is one of the ones you're supposed to have memorized, right? And then here I have the graph of its inverse, cube root of x. That's the other one you're supposed to have memorized. Oop, wanted to do that in red. There we go. So the reason that they're looking like that is because inputs and outputs are switched. So graphically, the x and the y values are switched. That's why they have this kind of similar look. Okay, then, come on, come on. There we go. Now, the only values that do not change are precisely the values where f of x equals x. That is the line y equals x, just like that. Because when the input is equal to the output and you switch the input and the output, there's no change. There's no change. So that's why here's a point where uh, x equals f of x. And here's another point where x equals f of x. So those points don't move. All the other points switch literally. So like this point here goes to there. This point here goes to there. This point here, oh, sorry, this point here goes to there. All of them are just reflecting across that diagonal line. Oops, sorry, this way. Yeah, I can't do it. Can't do it. Reflecting across that diagonal line. All right. So that's the basic idea. If you can graph a function, you can graph its inverse. All right. Oh yeah, this is kind of reiterating what I had said already. So this is true for any invertible function. So if you know your function passes the horizontal line test, yeah, you just graph it by reflection. Yeah, that's about it. Okay, now last thing we need to talk about are the cancellation equations. So these are really, really handy, maybe even people's favorite part about this stuff. Let's say f is a function. Then f inverse is the inverse of f if and only if these two equations hold. If and only if these two equations hold. One, f inverse of f of x equals x when x is in the domain of f, and f of f inverse of x equals x when x is in the domain of f inverse. So this is one that I need you to stare at for a minute before we talk more about it. So just look at it for a minute, think about it. Okay. All right. And maybe you can kind of see why these are called the cancellation equations. What's happening is these things are canceling, and what you're left with is the original input that you put in, right? Same thing here. These are like canceling, and you're left with the original input that you put in. So because inverse functions undo the process of a given function, if you compose a function and its inverse, you're literally undoing the process. So it's like going forward, but then backward again. What do you end up with? What you started with. Yeah, the inverse undoes everything. So yeah. Uh, an example I kind of like to use, I don't know if you have siblings, but here, or like younger siblings, here's an example. Let's say you clean your room. So you start with a dirty room, and then you clean your room, and the output, the result is a clean room. Then your little brother or sister comes in and they dirty the room up again. And so what you're left with is a dirty room. So it's like you are the forward function and your brother or sister, your sibling is the inverse function. You clean your room, and then your little sibling comes in and undoes all that cleanliness, and you're left with a dirty room again. So they literally undo the process. Um, the other thing about this is because this theorem is an if and only if statement, this is an equivalent definition of an inverse function. So this is another way of defining the inverse of a function. If you have some other function, let's say you have a function f and you have another function g, and you want to know if g is the inverse of f, you just compute these two compositions and see if you get x back or the input back. And if you do, then those two functions are inverses of each other. We're going to do that right now. Here we go. And this is one you're going to try on your own. So earlier in this section, we had inverted this function x cubed plus 2, and we found that this was the inverse, right? So what I want you to do is I want you to use these two cancellation equations. I want you to compute these to verify that these two functions are inverses of each other. All right? Think about that for a moment. Okay. Say something out loud. What are you going to do first? Right? And now try to work it out, and we'll do it together in a moment. All right, there you go. We'll do it now. Okay, so what we need to do is we need to take each one of these results and plug it into the other as an input and see what happens. So here, we'll do f inverse of f of x first. So we're taking f of x and we are putting it as the input of f inverse. Okay, so here's the formula for f inverse. Everywhere we see an x, we're going to replace it with f of x. There, right? So here it was x, now it's f of x. Okay, what is the formula for f of x? We have a formula for f of x. Oh, it's x cubed plus 2. So everywhere we see f of x, we're going to replace it with x cubed plus 2. So this becomes this. And now we can simplify. Plus 2 minus 2 cancels. Cube root x cubed cancels. And you're left with x. Yay! Right. Now we have to do it the other way. You got to do both ways. You have to check both orders. Otherwise, it's not an inverse. Okay. So now we're going to take f inverse of x and we're going to plug it into f. So the formula for f is this. It cubes the input and then adds 2. So we're going to cube the input and then add 2. What's the formula for f inverse? F inverse is cube root of x minus 2. So we're going to replace f inverse of x with cube root of x minus 2. Now we're going to cube that result. Those cancel. So we're left with x minus 2 plus 2. Negative 2 plus 2 cancels, and you're left with x. Boom. So that means that this is indeed the inverse function of f. So this is a way of verifying if two functions are inverses of each other. And that's about it. Right. On that note, let's play. That's right. So this is actually the end of chapter 2. So this is kind of the end of the general chapter on functions. We're going to see functions over and over and over throughout the course. You will see them over and over and over throughout your STEM career. We're going to explore them more, but this kind of rounds things out. So like always, I'm excited to work with you on these activities. Remember to ask questions, talk to the tutors, all that stuff. I will stop rambling, I suppose. And thank you again. I will see you in chapter 3. Have a good one, everybody.